Good day. So I'm presenting my work entitled Personalized Virtual Learning Environment Using Multiple Modeling Techniques. I'm Renato R. Maaliw III from the College of Engineering of Southern Luzon State University, Lucban, Quezon, Philippines. So for the introduction, so VLEs are fundamental cornerstones of most e-learning implementation of any modern higher education institution. So as the COVID-19 pandemic spread, an astounding 90% of classes are shifted online. So traditional VLEs or learning management system adhere to a one-size-fits-all approach by statically presenting learning objects without adapting to individual needs. So in recent years, there has been a recent increase in interest in adaptive or personalized e-learning. So what are adaptive BLEs? So it customizes the learning experience through differentiated instruction for each student who are participating in the course. So these systems are expected to identify the optimal course content based on individual characteristics. So there have been existing strategies for personalization, but mostly the common strategy is the cognitive evaluation, where a person or a student is tested on their prior knowledge. So while this is also very important, the diagnostic evaluation in order to adjust the learning materials or the learning teaching strategies. So it does not address the underlying issues that students acquire knowledge in different ways. So we have our own preferences on how we absorb information. So recent researches discussed promising results, but unified and comprehensive resolution is still needed. So data acquisition, so learner modeling, and the adaptation mechanism. So there are, based from researches, there is a sufficient proof that students learn best when the methods or material are tailored to their learning styles according to Kamparia, Amadaliev, and Wande. So what do we now know? So existing literature. So mostly it focuses on algorithmic advancement, but not on their system level applications. So there are proprietary adaptive VLEs. So there are the Newton's Alpha, the Smart Sparrow. There's also the Desire to Learn. But these systems are based primarily on rules. So the problem with rule-based systems is that they do not scale efficiently, and they are very deficient in interpreting unseen condition or the unseen data. So through existing literature also, so mostly systems adaptive mechanism is to redirect learning paths. So again, based on cognitive abilities through diagnostic exam. So if you have a poor result, so the system will recommend learning objects or learning resources based on your cognitive abilities. But it has a problem. So a more inclusive strategy must address the importance of learning styles in developing proficient adaptive VLEs. So according to our literature search, so there is no research that exists on combining learning styles, including their system level implementation. So our decisive contribution is the development of an e-learning system that integrated machine learning algorithms for learner characterization, and we also proposed a framework for adaptive virtual learning environment. So this research will benefit educators at any level with an innovative instructional approach that caters to different learners' characteristics and needs. So for our methodology, so we follow this learner modeling graph. So we collected learning styles result based from the our learning style model, which is based from the Felder-Silberman learning style model. So it has a index of learning styles questionnaire. So our learner uses a Moodle course. So we collected their interaction logs and we processed their information. We conducted feature selection. We benchmarked different classification algorithms to derive or classify their learning style. And when the model validation is accurate, so we stop the learning modeling. So what are our source of data? So as mentioned, so we utilize a Moodle course, specifically C++. We specifically tweak the content to have 86 learning objects over 6 chapters. So there are 1,028 students. So we have extracted 989,872 recorded logs spanning 8 years of 2019 to 2019. So again, we provided 86 learning objects with equal amounts of learning objects such as visual, textual, concrete, abstract learning materials. So we utilize the learning style model, which is again the Felder-Silberman learning style model. So it characterizes learning into 4 dimensions, such as processing, or the active or reflective learner, perception, sensing or intuitive, input, visual or verbal, understanding, categorizes in sequential or global. So a brief description of each characteristics. So for the processing dimension, so active learners prefer to digest information through application. They want to do something with the learning material. While reflective learners, based on the root word reflect, they mull over the learning content and they prefer to work individually. So for the perception dimension, so sensing learners prefer concrete learning resources with facts and data, while intuitive learner prefers theory, syntax, and concept or abstract learning materials. So for the input dimension, so categorized into 2. So visual, so prefers learning objects with graphic contents, and verbal prefers learning objects with text or audio. So for the understanding dimension, so when they access the course, you can see that sequential learners progress logically in linear way, so linear step by step. So while a global learner progress holistically, they tend to skip learning objects in significant gaps. So they skip learning objects. So for our feature mapping, so we select this feature based on the description or of our selected learning style model. So as you can see in table 1, so for the active learner, for example, they tend to post more on class forums. They tend to complete self-assessment tests and so on and so forth, as you can see in table 1. So for the global, for example, they view overview, outlines, and summaries learning objects. So we monitor their total visits. And we adopted a 30-second rule. So it means that a user to be counted as a view must spend at least 30-second rule, so that to avoid the random viewing of students. So some student view it randomly without reading. So to make sure that they read it, so based on literature, so it's only counted as a view if a student spend at least 30 seconds on the learning materials. And as you can see in figure 3, so we collected their number of interaction with a specific learning object. So for the data extraction, so we have 1,028 data, but we remove 96 learner and 34 because the 34 drop out of the course. So we also normalize the data. So it's very important that we have balanced data sets. So for the navigational sequence, so we use a linear regression in order to classify sequential or global learner. So greater than equal to 0.85 suggests strong linearity, and 0.85 for global learner suggests weak linearity. So the feature selection, so out of 12, so using information gain, so we remove the one variable for the processing dimension, which is the viewing of textual learning objects. So we benchmark different classification models. So SBM, base with the 70-30 training testing split. And also, we utilize hyperparameter tuning via grid search or the automatic tuning. So for the result, so we have different results based from different classifiers. So for the processing, so the SBM is superior. For the perception, the decision tree is superior. For the input, base 91.85%. For the understanding, so logistic regression, because of this variation, so we resort to tenfold cross-validated accuracy in order to measure realistically the accuracy. So based on our cross-validated accuracy, so the SBM is superior on three dimension, which is the processing, perception, and input. And the logistic regression is 87% on the understanding. But because logistic regression has the history of overfitting, so instead we use the decision tree, although there's also 1% difference of 86% versus 87%. So ROC plots suggest that the classification is not random, so the results is good. So we also deliver a comparative consistency test. So versus the manual classification of learning, which is the questionnaire based from our learning style model. So based on the machine learning prediction, it achieved closely 85% consistencies. So we also provided system architecture. So we do not stop on discovering accurate machine learning algorithms, but we embed the knowledge that we have to an adaptive virtual environment prototype. So we have several modules here. So the learner modeler module, the content adaptation for the adaptive mechanism for content, and the design adaptation module primarily for the navigation uh, adaptive mechanism. So as much as I want to discuss this in detail, so I think this is available on the proceeding, so you can read it there. Because of time constraint, I cannot discuss this one. So for the sample personalization implementation, so active versus reflective, we program that a self-assessment test for active learner be placed at the beginning of each chapters versus a reflective, which is at the end. So for adaptive content, so sensing intuitive, for sensing, so we supplement the contents with facts and data. And for intuitive, we supplement them with concepts and theories. So first, for the personalization implementation, so we have course content. So we supplemented visual learners, of course, with pictures. And for textual, so we remove the pictures. So in terms of course navigation, personalization, so since sequential learners learn in linear steps, so we limit their access so that they will not skip learning objects versus the global learners, which are learning through skipping learning materials. Okay, so for the discussion, so this research reports that student possesses different trees based on collected data from various sources. So we process 704,592 student interaction logs for spanning 8 years. So with benchmark classification algorithms, so cross-validation scores of 88% for SBM, for the processing, 86% perception, 87% input, except for the understanding dimension where the decision tree is superior with 86% procedure. So further testing on the generalization capabilities. So we also calculated consistent result, questionnaire based versus machine learning prediction. It has an acceptable mean of 85.49%. So this also proves that the learning style model questionnaire devised by Felder and Silberman is a valid instrument in unveiling learning styles. We then further extend the research by developing an adaptive BLE prototype, which focuses on learning styles based on sound system architecture. So again, our study is far from perfect, as we cannot capture other learners' tangible and intangible features, because the reality is that learning can happen anytime, even the outside the confines of a virtual learning environment. So for our conclusions and recommendations, so VLEs are prevalent and successfully implemented in most educational spheres, but it is built on the assumption that students are all the same. Often, the content experience is identical for all users, irrespective of their distinct educational needs. So we need adaptive BLEs to provide new engagement, which is necessary for the evolving and unique breed of learners that we have now. So with breakthroughs in AI, so we can revolutionize e-learning into flexible spaces by handing power to students rather than an authoritarian e-learning system with increased control over content and design. So within this study, we discovered accurate machine learning models for classifying learning styles in a BLE and embedding the knowledge into a practical prototype. So we firmly attest that this study has significant educational implications on the effects of adaptive e-learning on education as a whole. So for our future work, so we plan to improve the learner modeling strategies by including non-cognitive data such as grit, student grit, and evaluate the impacts of adaptive BLE in terms of students' academic performance. So thank you very much for listening.